Companies such as Kenny Waste Management, the industrial sponsor of this project, tackle the ever-growing problem of waste management. Waste from all over the country is brought to a centralized sorting facility where heavy and bulky materials are first removed by mechanical means. Magnetic separators remove any metallic waste, and ultimately, any remaining waste is manually sorted by hand at the end of the processing line. This sorting is a very physically intensive job. Workers have to work 12 hours a day, 6 days a week to sort this waste. Kenny Waste Management are having trouble finding and retaining a workforce for this sorting process. Any downtime in the sorting process has financial implications for them. While they pay to dispose of unsorted waste, wood sorted from this conveyor belt can actually be sold for a profit. Automating this manual process with machine learning and robotics will help solve all these problems. This is why we're proud to introduce Wiper. We set out to create a proof-of-concept robotic system that can detect, classify, and pick up small pieces of wood from a moving conveyor belt. The wood is of varying quality and different grades fetch different prices. We set ourselves targets of being able to distinguish at least 3 different grades of wood with an 80% precision and recall for the deep learning object detector. Once detected, the system should pick the wood from the belt, and this should work at belt speeds of up to 0.3 meters per second. The system also needs to be capable of being retrofitted at Kenny Waste Management. Our system consists of 2 distinct stages, detection and picking. As waste passes through the detection area, an overhead camera continuously captures detailed images of the belt. This camera is mounted on a custom stand with angled spotlights to evenly light the belt beneath. The images taken are fed into the system's software pipeline, where a deep learning algorithm identifies individual pieces of wood with their grade and position. The detection subsystem also uses these images to gauge the belt speed by comparing consecutive frames. For the deep learning algorithm, we trained a YOLO v5 model on our extensive dataset, which was built using images captured from the sorting plant and our lab. The system is managed by a centralized data processing server, which receives speed and object detection information. Using a calibration procedure, the system knows the camera pose relative to the belt. The data processing server uses this knowledge to correct any camera skew, and then proceeds to calculate an estimated time and position for when the objects will reach the robot. Based on the robot's availability, wood size, and grade, the server prioritizes and schedules objects to be picked to maximize revenue. In commercial environments, more and more management decisions are now data-driven, so we've implemented a database and dashboard allowing the system supervisor to visualize the plant's performance metrics. Using our interactive dashboard, the supervisor can automatically generate a rich array of charts with a breakdown by characteristics including grade, size, and date. The picking stage of the system consists of a robotic arm with a vacuum gripper. The robot receives the picking schedule from the data processing server and waits in position for the object of interest to arrive into the picking area. At a pre-calculated time, the robot lowers the gripper to intercept and pick the wood. Upon a successful grasp, the robot drops the piece off to the side. But how well does it actually work? With the current trajectories, the robot is capable of up to 7 picks a minute. The Achilles heel of the picking system was the gripper. Due to a tight budget, a low flow rate vacuum gripper was chosen, which proved to be ineffective in picking grade A and grade C wood. Design verification testing proved that the communications between the vision and robotic subsystems works as intended, as every successful detection resulted in the robot attempting to pick the item at the correct time. The detection subsystem developed can successfully detect and distinguish between 3 grades of wood with a less than 12% chance of mislabeling. Testing against images taken in the lab, the deep learning model met the target 80% precision and recall, but fell short testing against the images taken at Kenny Waste Management. We've identified future work that can resolve the shortcomings in this project. The performance of the deep learning model could be improved by using a broader dataset. Alongside the camera, a LiDAR can be used to 3D map the objects, giving more data points which can improve the algorithm's performance. A more powerful vacuum gripper can be implemented to improve the system's gripping reliability and expand the types of wood it can pick. In conclusion, this project has proved the concept of using deep learning guided robots to provide an effective solution to manual sorting in the waste management industry.